So I'm going to be talking about if not HTAP, then what? Because HTAP is great. It resulted in this conference where I have the honor of talking. It's also a really cool model, and it's really having a moment, as you know, as we heard. What I'm going to talk about is the other model, which actually the previous talk was discussing replication in this room. And so I'm going to dive in and talk about how that works. So a little bit about me. I think you can all read that font. I hope it's large enough. So I'm a database geek. I've been working on them since 1983. My day job, as it says here, is I run Altinity. We are an enterprise provider for ClickHouse. Run ClickHouse in the cloud, do a lot of open source work. And I'll tell you a little bit more about Altinity at the end, but for now, that's my background. Incidentally, everything I'm talking about here is open source. So you can grab it, try it out yourself, and have fun. Okay, so let me start at the beginning. Some of this is probably not necessary because people in this crowd are pretty sophisticated, but I think for general, if you're not, it's worth thinking about why different database types arise in the first place. And if you look at particular businesses, and we have over 200 customers, and they just do everything. These are just some of the things that they work on. For example, e-commerce. So if you're running an e-commerce site, you need transactions and transactional databases to do things like inventory management and purchasing. But at the same time, you want to understand what is going on when those transactions are being processed and to develop better strategies to run your business more efficiently. And so at the same time, sort of in addition to the transaction processing, you'll do things like funnel analysis to figure out, how people are flowing through your site, at what point are they dropping out of potential transactions, what can you do to sort of tweak it, to raise their interest. And of course, you're doing things like looking for fraud. And so these are two really different patterns of use of the database, as we well know. So on the one side, you have transaction processing, where you need to be very precise, very quick, may have high levels of concurrency. On the other side, you may actually have a completely different set of users, human analysts, and in some cases, software, which is running this analysis and then taking actions on it. So fraud detection is a good example of where an alert may get popped up to say, hey, this transaction looks weird, it looks out of, it's something unusual, so we want to look at it more carefully. So right now in the open source community, there's a number of databases that do each of these things well. I don't want to diss anybody, but I'm just going to focus on 3 databases for this talk, and in fact, mostly on 2. On the transaction processing side, in the open source world, the 2 big winners right now are MySQL and Postgres for just straight up transaction processing. They've been around for a really long time. There are literally millions of them running in applications today. So those properties, I think everybody knows pretty well. They include things like row storage, ACID transactions, very fast point lookups, very high concurrency, well, relatively high concurrency. On the analytics side, there's a number of contenders, but I'm going to focus on ClickHouse because that's what I work on. Does anybody here not know about ClickHouse? Okay, everybody's heard of it. You know exactly how the storage is organized, like that it's columns, parallel, across nodes, across cores, vectorized queries, sharding, high compression, all those good things. So these are the 2 standard databases that we find in a lot of deployments worldwide. And our customers, all our customers all use ClickHouse, but many of them also use these as well. So there are a large number of differences between these 2 types of databases, including not just ClickHouse, but if we widen the scope to Druid, Pinot, so on and so forth. But the fundamental difference is storage. I mean, that more than anything else determines what actually happens for query processing. So in Postgres and MySQL, all the columns are in a single row. Great for point lookups, but it means if you want to read 3 columns out of the table, for example, to read all values, you're going to need to scan every byte throughout the entire table. Moreover, it's rare in those 2 databases to have the blocks be compressed. and the compression is often not particularly good. So in MySQL, typical recommendation is not to enable compression because the overhead will slow down transaction processing. ClickHouse, on the other hand, columns. So we can obviously do column pruning. That phrase has come up in at least one talk I've heard today. A pretty standard technique, but there's more to it than that. The fact that you're storing data in columns with consistent data types means that compression is extremely efficient. So we typically see compression levels in ClickHouse of, if you do nothing, you get compression levels of 80 to 90%, but you can often get these up to 98 or even 99% in extreme cases. And what I'd like to show is just a simple example where we have some actual numbers. This is a numbers based on the on-time database. Does anybody know about that? It's a really cool sample database. It's airline flights. And this is running a query that reads 3 columns, and it's just asking, hey, how many flights in the last 30 years got canceled? And so it needs to look at 3 columns for that. If you were running this on MySQL, and the time that I was running it, the whole data set uncompressed was about 59 gigs, MySQL would have to read all 59 gigs using a single thread. So what would happen is when you do demos on this, because sometimes we would actually set up a demo, you would actually start the MySQL query in one window, and then you would come back about 20 minutes later and note that it hadn't finished yet. It's so slow. Now, if you read it in ClickHouse, you just read 3 columns, and that already, through the fact that you prune off all the columns you're not interested in this table is about 109 columns, that gets you down to 3% of the data. So that's already a big win, but the really big win is from compression. So in fact, the actual amount of data that we really read was only 21 megs total. We're dropping this down by 30 times when we get, just by pruning columns. With the compression, we drop it further 100 times. So we've already reduced the amount of data by 3,000 times. And then, of course, we parallelize it, because ClickHouse, like most data warehouses, is very good at parallel query. And so in fact, each thread only reads 2.5 megs. Yes?
Do you need 8 threads to build 3 columns?
No, actually, you could just read it with 1. This just happens to be, I was running on a machine with, I think, 16 vCPUs when I ran this. So ClickHouse defaults to just using half the available vCPUs. You can actually play with this number as to your heart's content. Was there a deeper question behind that? Or?
No, actually, what I was wondering is, will 8 threads be too many threads to build just 3?
Excellent question. It depends. It depends on the amount of data that you're scanning. So ClickHouse tables, as I'll show a little bit later on, are split into parts. ClickHouse is very good about parallelizing, so that it'll scan one part in parallel with another part with another part. So there's 2 things that depend on how much benefit you get from the threads. Is the data spread out enough that most of the cost can be put into the scan? And then the second is you have Amdahl effects. So depending on how you write your query, there may be some merging and sorting at the end.
Could it be multiple segments?
Yes. Yeah, so the parts are segments, exactly. So you can play around with this number. Generally speaking, ClickHouse is going to try and parallelize the scan part as much as possible. And then the final merge and sort tends to be more single-threaded. But there's also parallelization there. So this is a huge difference. And one of the things that which will come up is that ClickHouse gives you, like a lot of custom, sort of databases that are focused on data warehouse, it gives you a lot of knobs that you can twist to make this go, play with the number of threads, play with the sorting, play with codecs. So you have a lot of power to really optimize this search. And that'll come up in a minute. So there are some reasons not to use HTAP, and I think this is interesting for us because in some sense we're on the other side of the fence. PingCAP is serving one part of the market, we're serving another part. So why is it that people wouldn't be using PingCAP? And here are 4 reasons that actually come up pretty commonly. One is many of the systems that use MySQL were not built yesterday. They were actually built a decade ago. So these are systems that have been running for years. They already work, and there's just there's no gain in trying to migrate these things. So that's a pretty common one. Another thing that's kind of interesting is, and it'd be interesting to understand how PingCAP deals with this, but a lot of times you have you have multiple upstream sources. And I'll show you an example of that in a second. So you have many things that feed into the data warehouse. It's not just your transaction processing. Another thing is that there are just some cases where data simply belongs in an analytics store. You're never going to run transactions on it. I'll show you some examples of those in a minute. And then finally, this is kind of an interesting one that I didn't really think about, but has come up as we've been getting into this problem, is as you get into these big corporate bureaucracies, it turns out the people that do the transaction processing are a different department from the people who do the analytics. So, and I don't know how PingCAP deals with this, because you'll come in and you have two groups. They may even be fighting with each other, and so it's very difficult to get them to use a single solution. And we've actually seen this ourselves as we're trying to, as I'll show you, we're sort of replicating data out of MySQL into ClickHouse, and we innocently thought, hey, we could just go and tell them, hey, we've got this great solution. And what we found out was, no, you actually have a completely different team that we don't even know their names, who actually do the analytics. And so
quick comment. My use case is actually fall into this three circles here.
Yeah. Oh, really? What is your use case?
I have multiple upstream sources for sure.
Yeah.
And I have different owners for OLTP and
yeah.
OLAP. And I also have this one.
Right.
Some of the use cases belong to specialized OLAP database.
Right. Yeah, so I think what this means is, I think what we're going to see is both of these solutions are going to be used, but the market is, because this market is very broad and people use data in very different ways. And here's an example of the life is messy picture, and I don't know if your picture looks like this, but this is actually one of our a former customer at this point. But this is what their system looks like, and I left a bunch of stuff out. So just because it started to get really hard. But two things to notice about this is here, multiple upstream sources, all of which is getting fed in. And not only the upstream sources, but it's not all transaction data. So clickstream events, every time you touch something, like in some cases, even as you're wiggling your cursor, an event may be generated coming back through some sort of event listener, fed through Kafka and read into the data warehouse. So that's one thing that's kind of striking here. The other thing is that ClickHouse, or whatever you use as the data warehouse, is the linchpin of this system. So it's not just that all the producers are feeding into it, all the consumers are coming out of it as well. So to be able to turn this, to use a different database is going to be hard, because you're actually talking not just changing ClickHouse, but changing a bunch of apps, both upstream and downstream, that consume from it. So this is a reason why actually a data warehouse, why thinking about using these things together is something that's going to be a persistent issue for a long time, which means the same thing. Okay, so that's the intro. I'm going to talk about two patterns that we see for using these systems together. I'm going to try and keep it really simple. You can make it more complex. But, here we are. This is just a table of stuff that we look for when we're trying to say, hey, you might benefit. You've got transaction processing. You might benefit from bringing in an OLAP database. So the first thing is, and I saw this quite a bit when I worked on MySQL. I worked on MySQL in that community for a number of years. Huge tables of immutable data. So good example, we worked for a company we had Marketo as a customer. They're really big in marketing campaign management. And they would have tables to do your campaign management, which is basically transaction processing, defining the campaign, defining the elements in the campaign, defining sources and stuff like that. But then they would also have all the events generated by the campaign. So you would literally go in and you'd see a bunch of little tables, which might be like a few million rows max. And then you would see the events table, and it would be hundreds of millions, if not, closing in on 1 billion rows. So when you see this in MySQL, that's a sign you might want to peel something out. Another thing that's kind of a hint that you probably want to be considering using these two things together, whether PingCAP or sort of bringing an OLAP database, is that you have complex aggregation pipelines. The thing that MySQL and Postgres cannot easily do is they can't answer general questions without pre-aggregation. So if you think about the cost of a table scan and the cost of doing aggregates like counts or histograms or things like that, in MySQL, what you'll find is that if people are using MySQL, they've got a bunch of extra processes that pre-compute the answers to these things and then dump the data back into MySQL. So there'll be a batch process that runs at night that pre-computes all the aggregates. If you see, and these pipelines are messy and they're slow. And then finally, a lot of times you'll just see questions that aren't answered. People won't be able to do funnel analysis, for example. It's just too hard to do. The queries are too slow. It's not worth doing. So there's a couple of solutions. One is just to migrate some of the data out of MySQL or Postgres and stick it in an OLAP database. Let's look at that. And I'm going to use specifically MySQL as the example here, but the same thing applies to any other transactional database. And the point here is that, as I said before, some data just belongs in an OLAP store. You're never going to run, like web access logs. There's no transaction processing on these things. They're generated once. It's immutable data. It's just facts. CDN telemetry, market tick data, all this stuff. These are things that trying to funnel it through any kind of transactional is kind of a waste of time. So it bogs them down, and also it makes for a more complex system. So in that case, if you put it somewhere else. And so this is a pretty common pattern that we see, is that you'll start with an end user application, MySQL, and for example, the Marketo example I mentioned, very big fact tables stuck in there, a bunch of back-end processing tables. Those can continue to live there, but what we're going to do is basically just do a dump load, bring them over, and put only the tables that we really need to do analytic processing on in ClickHouse. And then we're going to do something kind of interesting here. We're actually going to use ClickHouse's ability to look back at and actually read MySQL database tables, and we can actually join on the MySQL data. And I'll show you how that happens in a second. And then basically you just extend your application so that instead of calling MySQL for the analytic queries, it just goes straight to ClickHouse and asks the questions there. This sounds complicated. It's actually not. Because you basically have to tweak part of your application to know where to connect to, but it's not that hard to change the queries. The types of things you do, group bys, sorts, stuff like that, are all pretty standard. So here's an example of creating the table. And what we'll use is a standard ClickHouse engine, which is called merge tree. That's our big data table. It is very, very good at dealing with large data sets. The create table is basically the same where it says string in ClickHouse. You can also say varchar 250, and it will internally call it a string. Examples of some of the tweaks that you can do is you can really play around with what I'm doing right here is I'm overriding the compression. By default, we use LZ4 compression. I'm overriding it to be ZSTD1, which is really good. Various levels of ZSTD are good for ints. Here's an example. I've got a date time. I'm going to actually use what's called a delta codec. What a delta codec stores is within the column, instead of storing the successive values, we store the differences between successive values. So this will compress the data down, and then we apply ZSTD compression on top of what remains. This is the kind of thing which will get you 99% compression. And the reason is that we've got an order by in this table so that these values are guaranteed to be monotonically increasing. And then there's sort of other things out there. Otherwise, it's pretty standard. So what's interesting to look at, if you haven't looked too deeply into ClickHouse, is why is that fast? Well, because of this merge tree table. Basically, what's happening is it's columnar storage. There's what's called a sparse index. So in this table, we're actually ordering by it. So we will actually have an index created on timestamp. Normally, you put more values in there, but I was kind of lazy on this one. And then that will help us locate blocks so that any query on that table where we have a predicate, like a filter by condition that's based on the timestamp, it will zoom in and basically, like we want to read a range of values from yesterday, it will zoom in and find the blocks efficiently. And then skip indexes, which tell us which blocks we can skip because we're not likely to find values, Bloom filters, set indexes. These are various secondary indexes to make that search more efficient. And then, as I said, the data is sorted, compressed, and then indexed from the sparse index. The reason this sparse index is important is that, unlike MySQL or Postgres, the indexes in ClickHouse are designed so they always fit in memory. And that's important because if we're dealing with 1 trillion rows, which is pretty easy to store on a single node, you want that index in memory because then you can quickly zoom in and pick off the blocks. So that the sparse index only has, by default, has entries in it every 8,000 rows. Now, one of the interesting capabilities of ClickHouse that makes it ideal for working with MySQL and Postgres is it can actually look back and read MySQL. And there's a thing called the MySQL database engine where you can define a database and you give it a name, and then you tell ClickHouse, hey, where's it located on MySQL? And basically, at that point, every table within that database becomes visible to ClickHouse and queryable. So this is super useful because...
So are you creating a read replica of the primary MySQL?
No, actually what this is doing, it's just looking straight across. It's a TCP/IP connection, and it's just reading the tables directly. And strangely enough, this is faster in some cases than running the same query in MySQL. And the reason is ClickHouse is super good at aggregations, and it will parallelize to a certain extent. Plus, the merge and sort are very, very fast compared to MySQL. So here's an example of how we set that up. So we just say create database. If you've used ClickHouse or if you've used MySQL, this will look kind of familiar. We just create this database. There's its name. Here's the engine type, that is to say the access methods for this database. And I just type in this stuff. You don't actually have to put the password in. There are ways of getting around that. And then you can do a show tables, and bang, they all show up.
This happens on the ClickHouse part.
This is on the ClickHouse side. Yeah, exactly. And so I had a bunch of tables there. I just showed 2 interesting ones. And then what you can do is 2 things. First of all, this makes dump and load really, really, really simple. There's various ways you can dump and load data. There's about 3 good tools that we use. But another thing, just to illustrate this, the power of being able to see into MySQL, is we can just go ahead and select the data straight out of the MySQL table, using this connection, and then use that to feed and insert to go into the new table in ClickHouse. So we do this, and there's various ways you can add a little tooling around this, make it run in parallel, make it divide things up into chunks, but this copies your data over. So you don't even have to, like if you're up, and the reason this is interesting is if you're up in the cloud and you're doing this kind of transition, what you'd really like to have is your MySQL running the cloud and ClickHouse running the cloud talk to each other directly, not working through something like MyDumper or MySQL dump, which forces everything to come through your client. Yes?
How do you handle data type differences?
Actually, in general, ClickHouse more or less understands the data types between systems. There are cases where you actually have to go tweak things. Good example, floats. You sometimes have to define them a little bit bigger on the MySQL, on the ClickHouse side to make sure they come over. There's also things like date time, which it turns out it's the very worst case. It's not like one is a proper subset of the other. They're actually overlapping sets.
But you have to use ClickHouse on how to do some conversion? Or?
Yeah, what I usually do is when I'm doing one of these migrations, I'll pull the data over, sort of, and then check the data types, and then I'll tweak the schema to make it work. We're working on tools to make that automatic.
There's actually a faster way to load it if you use the new infrastructure in 8.2.
In MySQL?
Yeah.
Oh, the MySQL shell?
No.
What is it?
We can talk about it later.
Oh, yeah, I'd love to hear that. Okay, so, and then here's the example of the join. So this is an example where, and this is ClickHouse syntax. What I'm doing here, ClickHouse doesn't have a cost-based optimizer. So the great thing is you won't be confused about what the cost-based optimizer is doing. The bad thing is you got to do it yourself. This is an example. This query is written in such a way that ClickHouse, because it's a subquery, ClickHouse will know, hey, I need to run this scan, and then I go and join against MySQL. The important thing here is this actually, it runs more efficiently because we don't bother to join with the MySQL table until we have a reduced subset after aggregation is complete. But the point is, this is the live MySQL table. It could be updated through transactions. It's going to be the current copy that's used for this join. Okay, that's migration. Yes, question?
What kind of resource pressure would it put on MySQL?
Well, basically what it's going to do in this case, what it's going to do is it's basically going to, that's a really good question. You know what I do? If I'm not sure, I'll tell you what I would do in this case to answer your question. I'd turn on the query log if it weren't turned on already in MySQL. I'd run this query and see how much of, see if it pushed down filters.
You talked about inserting data in ClickHouse, select from MySQL.
Yeah.
And you talked about options to include more threads.
Yes.
Would those threads put CPU pressure on MySQL?
Yes, they would. If you're running in parallel, you're definitely going to be, at that time, you're going to be hitting up MySQL pretty hard. So in fact, in a live system, what I would typically do is do that load off a replica.
And does it rely on any sort of logging that needs to be enabled?
You mean inside MySQL or like bin logs?
Inside MySQL, do you need to enable some?
No, nothing. That's the cool thing. This thing will just connect and work. You don't have to make any changes to MySQL at all. It's a really cool feature. I mean, there's a lot of things about ClickHouse that are not great. I'm going to make sure I talk about those, but this one is really good. So in fact, here's an interesting thing. If we were doing this, what I might do is I would probably see, ClickHouse is not smart enough to figure out a way to move this over so it could help with the MySQL query. I might do a little work to actually put some additional conditions out here so that ClickHouse can actually see and hopefully push down to MySQL to make that query less expensive. There's another important way that ClickHouse can see MySQL, which is to use something called a dictionary. And if this tenant ID, actually, my assumption here was a tenant ID table is small. I mean, how many people have thousands of tenants? Well, some people do, but even thousands of tenants is not that long to scan. So I'm assuming this is going to be cheap. If it's not, I'll action to fix it.
So there's no way to give a pushdown predicates or something into MySQL itself?
Actually, ClickHouse, I was surprised. I played around with this. I was surprised to find that filter conditions will get pushed down. If ClickHouse can tell that the filter is applicable to the table, it will push it down. So, but that's why the query log is important to go see what's going on down there. All right. Here's pattern 2. So first way of coupling these two things was just, hey, we got OLAP data. It's like marooned in MySQL or Postgres. Let's just move it to its proper home. There's another case which is more like what you would be doing with PingCAP, which is, hey, I've got transaction data and I want to know more information about it. So for example, you just want a copy of it in a column store. And here's a bunch of examples that, of things where you're doing transaction processing. Take chat messages, for example. Transaction processing, you don't want to lose them. You like ACID transaction model, but you'd also like to do analytics on them. So you want a copy of them just in a column representation. Financial market transactions, another example. So that's actually it turns out that's one of the use cases that's driving the work that led to this talk. So here's how you do that one. Just like in the previous talk, for anybody who was here in this room, you're going to do two things. You'll do an initial dump load, and then you will read the bin log or the WAL, or whatever log the database offers, and then you're going to use some sort of real-time replication to bring it over. You can use things, other things that are non-real-time. I think those are less interesting for a variety of reasons. Most of the applications we work with, people want to have this stuff over here and analyzable as quick as possible. So, so far, this is pretty standard. What's interesting is with ClickHouse, like most data warehouses, is very slow to delete data. So if you have rapidly mutating data in MySQL or Postgres, you need to find a representation inside ClickHouse that can store it and deal with those mutations effectively without dragging down the database or just being slow. And in ClickHouse, we have something called the replacing merge tree. It is a variation on this merge tree structure that is designed to deal with updates. It has a couple of extra fields, one called version and one called sign. I'll show you what they look like because it's easier to show it with a picture. Here's another thing. Basically, when you're mutating data in MySQL, and I'll stick with that example, you have a primary key. Here's the primary key. So this identifies the row. Another interesting thing that we do in MySQL is in this particular table type, this order by, every unique combination of these values identifies a row that can be mutated. So basically, we allow the sort order to help guide us to group the data together that's potentially going to mutate and need to be resolved. So that has an interesting consequence that I'll show you in just a second.
We talk about something similar to SM tree.
This actually is not. It's a different idea. The idea here, and let me just show you this table, because I think if you said LSM tree? Yeah, this is a little, merge tree itself is kind of reminiscent of an LSM tree. It doesn't have the in-memory part up front, but this is a little bit different. So the idea here is that in large distributed systems, another way to deal with mutations is actually to use a sort and not make any assumptions about how you're going to find a row and update it. Instead, you're going to ensure that when people run queries, you actually resolve to only get the last row, only get the last update. And that's basically how this works. So this table type, if you put the row in the first time, you'll have a version on it, and you will say, hey, 0. That means that's the first one. If ClickHouse doesn't see any other version that's associated with this film ID, category ID, and distributor ID, that's what you'll always see in queries. But let's say you do an update. What you add to this table is, you'll call it version 3. You can compute it off the bin log or something like that. Anything that gives you an increasing version number. And what we'll say is we'll add a row that says 3 and a -1, and then it has 25 and the other two values, and then a row that says 3 and +1 and 25 and the other two values. And the way that this is interpreted is that when the replacing merge tree reads this, it will actually come down here, and these two are guaranteed to be in the same part. It will see this last one and says, the last value is whatever was in this row.
What's the sign?
Okay, the sign is basically to tell, this is adding a row, this is subtracting a row. And this is important because when we do an update, I said that to make ClickHouse perform, we also need to sort in other ways besides just the primary key from MySQL. This could change. Like this is not part of the primary key. So what we're really saying is, hey, maybe the update was to change the category ID. What could happen is we'd have category ID 1, so this is taking that row away, and then this is category ID 2. It's adding a new row. Does it?
Like NBCC.
You know, it has some, yeah, these ideas have been floating around for decades. But the point is that at any given time, you know, when you run a query, as long as you sort the data and look at the last row, you'll see the final state of the table. Now, there's a couple costs associated with that. Well, there's some costs associated with that because doing this computation is going to take 5 minutes. Okay, good. I'll be done in 5 minutes. Doing this computation is going to be expensive on every query. So what we do is we merge. So ClickHouse, like any self-respecting columnar store, it has parts. They get loaded in. And what we're going to do in the background is we're going to merge those parts and resolve this data. So in fact, this particular one, you know, if we look at the first two updates, the insert and then the update operation, when they merge, it just leaves this row right here. So no extra cost to find out what's the state of the row. However, merges happen in background, so they're not guaranteed to have happened. So we actually need to have a way of telling the query, hey, you know, like if there's anybody else who hasn't been merged, do the sort and make sure that we're getting the right value. And there's a keyword called final, which we put in that does this. And what this does is you take a performance hit for this, which varies. You have to be, this is the part where this becomes a little bit difficult. You need to organize, you need to be very careful about optimization, but you have this, and basically there'll be an initial scan that merges the rows, and then we'll apply our aggregates on top of that. No, actually what it will do is, it will take the blocks in whatever state they are, and it will do the final, it will be as if they had merged completely. Yeah. One final thing is these -1 rows, those are deletes. We don't want to see those. Who wants to see a deleted row? I mean, it's gone. So we have a feature in ClickHouse called a row policy, which is really a security feature. Actually, what it does is it just says, hey, if the row that ends up being left over after that scan has a -1 in it, don't show it. Don't let the user see it. So as a result, with these three steps, background merges, being able to force a merge in the query, and then subtracting out these -1 things, you basically see an accurate picture of the updated rows. This is more costly than going in, you know, for the query than going in and updating the rows. But the thing is, you won't have to pause ingest. You don't care where the rows are located. They could be on different machines. This algorithm works. So it's kind of an interesting way of solving the problem. And what that leads to is, this is the fully wired continuous replication. So the initial dump load, we use Debezium to pull stuff out of the bin log. We've tested it. It's okay performance, which is to say we can get it running right now at several 100,000 rows per second. ClickHouse can load data at tens of millions of rows per second. So there's still performance work to be done here. And then we've developed a component called the Altinity sync connector, which Debezium drops it into Kafka or any Kafka compatible event stream. The sync connector will then apply it to the tables. Okay. So some things that are, the slide that was missing here, some ongoing work. That final keyword is kind of a pain. So we actually have a PR in that's in review to just make it be added automatically to tables. Hopefully that'll get in pretty soon. There's other work from a French company called Content Square, which is taking care of making all those deleted rows disappear automatically. So that, there's good progress on that. I expect that will be in a matter of weeks. So basically some of the little quirks that I showed you are going to be eliminated. The final thing is to work on performance, and that I anticipate is something that will take time.
What if you don't want to take the hit at query time for doing final?
You can do, you could force optimize table. The other thing you can do is make the hit as small as possible. There is a feature, for example, you can partition data there's kind of a trick where you can build partitions by time, and if the assumption is the changed rows will never cross a time boundary, you can actually cause ClickHouse to not merge older data. Did that make sense, what I just said? Yep. There's actually, you have to Google the parameter or look for it in the code. All right, So this is pretty obvious stuff. Here's how to find out more. So the ClickHouse repo to find out about ClickHouse. The Altinity sync connector for ClickHouse, that's software that enables us to work with MySQL. And we are extending it to, as soon as we really get that one nailed down, we'll do it for Postgres followed by Mongo. And then the Altinity blog, where there's a big article that summarizes everything that I talked about in this table in much more detail. And that's, oh, and we're hiring. Where is it? Somebody took it off. So anyway, we run a cloud. We do support. We build ClickHouse. You're welcome to visit us. We'd love to talk more about this. This is a problem that really interests us, and we'd like to help as many people as possible. Thank you very much.